Alright, so today we're going to be talking about the first derivative test. So the first derivative test is a way that you can test to see if an equation has any relative minimum or maximum points. So this is useful for finding relative extrema. So far you should know how to find relative extrema just by looking at the graph of a function. So previously in your math classes, including this one, we've talked about relative extrema or local extrema. This is whenever you have a local minimum or maximum point. So you should know how to find a relative extrema just by looking at the graph. So there's definitely going to be a relative maximum point right in this area. So if you look to the left of this, we're going uphill. And then when you max out on that, you stop going uphill, there's a moment where you're not going uphill or downhill. That is your relative extrema. That's a maximum point. After that, you're going downhill into this valley, and then you hit a minimum point. And then after that, you're going uphill again. So that's how to find relative extrema if you're looking at a graph. But let's say if we don't have access to a graph and we just want to find the relative extrema only through analytical means. So let's think about what's happening to the derivative as we move along this graph. So moving from left to right, notice that this cursor is getting higher and higher. Well, in terms of a derivative, if you're increasing, that means that your derivative is positive. At the top here, we hit a maximum point. That would be a relative max. After that relative max, we are decreasing. We're going downhill. So when we hit the bottom of the valley here, that's when we find a minimum point. So there's this one instant where you're neither increasing or decreasing. So that's when you're at the minimum. And then after that point, you're going uphill again. So our first key point about derivatives has to do with the slope. So we saw that we were increasing over here. And as we were increasing, that meant that our slope is positive. So that's the first takeaway. If f prime is greater than 0, so if f prime is positive, that means that your function f of x is increasing. So we're looking at the derivative to show something about the function. And then on the other hand, if f prime of x is less than 0, so f prime is negative, that means that f of x is decreasing. So now let's look again just at this maximum point, and let's think about what's happening around this maximum point. So we know at the maximum point itself, you're neither increasing or decreasing. So you would have a 0 slope of the tangent line right there at the top. So since we're increasing from the left, that means that f prime of x is positive to the left of this maximum. And then it's decreasing to the right, that means f prime of x is negative to the right. So that's our key takeaway number 2. If f prime of x changes from positive to negative at some point x is equal to c, so remember c is going to be a critical point here, then that means that there is a relative maximum at your critical point x is equal to c. So in the example above, we had a maximum where the f prime of c was equal to 0. So there was a horizontal tangent just at the top of that hill. And if you look to the left of c, over here to the left, your graph is increasing. So over from the left, f prime of x is greater than 0. And then to the right of c, it's decreasing. So f prime of x is less than 0. So that's how to find a relative maximum if your derivative is equal to 0. But what happens if your derivative is undefined? So that happens if you have a cusp or a corner. So if you have a cusp or a corner, that means f prime of c does not exist. Well, it turns out that even it doesn't matter if it exists or not. To show that it's a relative maximum is actually the same. If to the left of that point where it doesn't exist, if your slope is positive, that means f prime of x is greater than 0. And to the right, if the slope is negative, that means f prime of x is less than 0. So if that's true, that means that you still have a relative maximum at that point. So this method works whether f prime of x is equal to 0 or if f prime of x does not exist. So let's look at our graph again, and let's focus on this minimum point. So f of x has a minimum point somewhere in this area. And if we look to the left of that minimum point, the graph is decreasing. And then to the right of that point, the graph is increasing. So that's how we can find that you have a relative minimum. So this is our key point about derivatives number 3. If f prime of x changes from negative to positive at some critical point, x is equal to c, then that means that there is a relative minimum at x is equal to c. And once again, this works whether f prime of x is equal to 0 or if f prime of x does not exist. So if you find a point where f prime of x is equal to 0, and if you look to the left and see that f prime of x is less than 0, that means it's decreasing to the left. And then to the right of that point, x equals c, if you find that f prime of x is greater than 0, that means that it's increasing to the right. So that would show that you would have a minimum point at x is equal to c. That also works if f prime of x does not exist. Look to the left if f prime of x is less than 0. Look to the right if f prime of x is greater than 0. That means that you have a relative minimum at x is equal to c. So there's one other situation that we haven't discussed yet. What happens if you have a horizontal tangent, but the signs do not change on either side of that horizontal tangent? So let's take y equals x cubed, for example. If I take the derivative of y equals x cubed, that would give me 3x squared. So if I set that equal to 0 to find the critical point, that means that x is equal to 0 is a critical point. And notice that right here, it does look to be true. I do have a horizontal tangent at x is equal to 0. But at this point, this is neither a minimum or a maximum point. And the reason why is because the sign doesn't change around it. So here in this example, I'm increasing from the left. I hit a horizontal tangent, and then I'm increasing to the right. So this point, x is equal to 0, can't be a relative minimum or a maximum, even though it was a critical point. So when that happens, this is called a saddle point. And so this is key point about derivatives number 4. If f prime of x doesn't change sign at x equals c, then there is a saddle point at x equals c. So to the left and to the right, f prime could be both positive or it could be both negative.